So here we have to use a ratio test to determine if this series converges. Now, I want to ask myself the same problem. So what if the problem didn't tell me to use a ratio test? Is there a way for me to determine what's the best test to use? So let's look at the numerator. It has a factorial. So typically, of course, this doesn't work all the time, but it works most of the time. If I see a factorial, I should think about using the ratio test. As we'll see when we work through this problem, that when we use factorial and ratio tests together, there's going to be a lot of cancellations. Okay, let's go back to the problem. We want to use a ratio test. We have to take this ratio on the right. So let's write out what a sub n plus 1 and a sub n are. So a sub n plus 1, well, again, I want to mention that we can omit the absolute values because these terms are all positive. Okay, a sub n plus 1 is 2 times, instead of n here, I have to have n plus 1 factorial over, now I replace all the n by n plus 1 over e to the 2 times n plus 1. Now, I want to simplify this a little bit. It becomes 2n plus 2 factorial over n plus 1 over e times 2n, to the 2n plus 2 power. Now, I want to rewrite this again because I see too many fractions here. So I just multiply the numerator and denominator by e to the 2n plus 2 to write this as 2n plus 2 factorial times e to 2n plus 2 over n plus 1 to the 2n plus 2. Okay, so what is a sub n? A sub n is just what we have here. It is 2n factorial over n over e to 2 to the n. Again, I want to do what I did over here so that I have one fraction. Then this becomes 2n factorial times e to the 2n over n to the 2n. So now we have to take the ratio of an plus 1 and an. An plus 1 over an is equal to, well, let me just copy down what a sub n plus 1 is. Now, dividing by an is multiplying by its reciprocal. So the reciprocal of an is n to the 2n over 2n factorial e to the 2n. So let's see how we can simplify this. You see, we have e to the 2n plus 2 and e to the 2n. Well, that gives us e squared. And let's keep going. So we see 2n plus 2 factorial and 2n factorial. That gives us 2n plus 2 times 2n plus 1. All the other terms cancel. Lastly, we have n to the 2n and then n plus 1 to the 2n plus 2. So I'm not exactly sure what's the best way to write this. So I'm just going to write it like this. So I'm going to write it as n over n plus 1 to the 2nth power. So I took care of the numerator. And the denominator has 2 more powers of n plus 1. So times 1 over n plus 1 squared. So I want to simplify this even further. We write it as e squared, 2n plus 2, 2n plus 1, over n plus 1 squared. Now times n over n plus 1 to the 2n power. Now, this might look a little familiar because it's really similar to the definition of e. Now, recall that e is actually defined to be, the limit as n goes to infinity, n plus 1 over n raised to the nth power. So if we take the reciprocal of this on both sides, we get 1 over e is the limit as n goes to infinity, n over n plus 1 to the nth power. Now, we just need to square both sides. We get 1 over e squared is equal to the limit as n goes to infinity, n over n plus 1 to the 2n, which is exactly what we want. Now, it's not hard to take the limit of this term as n goes to infinity. So let's do that. Let's take the limit as n goes to infinity, the absolute value of an plus 1 over an, all terms are positive, we can ignore the absolute value, is the limit as n goes to infinity. Well, this first term, e squared, well, let me simplify the product quickly. It's 4n squared plus 6n plus 2. The denominator is n squared plus 2n plus 1. And then we already did the limit of this as n goes to infinity is 1 over e squared. So good news is that we can cancel these two out. Now, we know what the limit of this is. This is simply equal to 4. How do we get that? We just apply by applying L'Hopital's rule twice. Now 4 is clearly greater than 1. So we go back to the ratio test. This is the second case. So we can conclude that the series actually diverges. Okay, I'll stop here.